Hello, my name is Richard Pham, and this is Lab 5, Falling Slinky. For the introduction, the purpose of the lab was to use Newton's second law, or the momentum principle, and the force of drag and tension to calculate the differences between observed position and computer models. The object was a Slinky, its environment was air and earth, the observed model was used to tracker, computer model was used to gyroscope. And the results are that using the momentum principle to calculate the gravity and tension, creating a position versus time model when the spring is stationary, then using momentum principle to calculate the gravity and drag when the spring is moving, to compare data from the observed and computer to understand why the spring is stationary even though gravity is acting upon it. The main physics ideas was Newton's second law, which states that the change in an object's momentum over change in time is equal to the net force acting upon the object. This is a kinematics equation stating that displacement is equal to initial velocity times time plus 1/2 acceleration times time squared, which can be used to derive the position update formula. And this F drag is equal to negative b v squared v hat. Initial conditions. The Slinky was guessed to be 0.25 kilograms and placed at a certain position where known height of Derek was 1.78 meters, and the origin of our axis was placed at the bottom of the Slinky. The high-speed camera was running at 300 frames per second. Its initial position was at 197 frames, which was 000, and the final position was 677, was negative 0.520 meters. And the system is linking on Earth for gravity and the Slinky, and the surroundings was the air, which we eventually calculated for force of drag. This is the tracker model, and as you can see here, there was a lot of frames to drop on. And here we use the axis as 1.78 meters for the calibration stick here, and just plotting a bunch of points. For the coding, so this is the initial conditions that I stated, ball being 0.25 kilograms, the ball position being 0, 0, 0, placed at the origin, the time was 0, and delta t was 0.01, chosen for accuracy, and the gravity is 9.8. This is the unit vector for positive y-axis. B, the coefficient for force of drag, was calculated using trial and error. The t less than 1.00077 was calculated by finding out the frames between the zeros, how long it stayed at 0, the position at the origin for, and dividing that by 300 to calculate the seconds. And the rate's at 100. The weight is the ball mass times gravity times the unit vector, and negative because it's going in the downwards direction. And force of tension is equal to the opposite of weight, which is calculated because we know that there has to be a opposing force to gravity at the bottom of the Slinky, because Newton's second law states that if there's an unbalanced force, then an object, or actually Newton's first law states that if there's an unbalanced force acting upon the object, then it has to move. And since it's balanced and staying stationary, that means that the net force has to equal 0, which is why its force of tension is negative W. And F net is just W plus F of T, and ball velocity is calculated by doing the change in momentum over change in time, so ball velocity plus the F net divided by mass times delta T. And ball position, this is just position update formula, position plus the velocity times delta T. And this is practically the same for this. This was 1.63 seconds for the end of the trial, and the weight is the same, but the force of drag is different. This is calculated using the negative v squared times the velocity vector, and then F net is just weight plus force of drag, and same as the code before. So Newton's second law is ball velocity here, and position update formula for ball dot position, and then this will result in the two models. So as you can see here, the predicted model and the observed model are practically the same. There's a bit of a spike here, which is most likely caused by errors from the angle here. As we can see here, from the bottom up to Derek, this is not completely straight and vertical, which could cause some errors here. But also, due to how many frames we were clicking, there's definitely a error on just a tracker error from personal usage. And what does it mean? So how does this thing stay in the air? I can see from this graph, there's a tension force pulling each part of the spring up as the force gravity is pulling it down. And since it's at the very bottom is stationary because all of this tension force from all of the springs is pulling it up, which causes the bottom to stay stationary, while the here where the force of gravity is pulling on the top ones, the force of gravity is enough to overcome there's not tension force at the very top, which causes the top to fall first and causing a graph to pull down. And so what if we attached the weight to the bottom of the Slinky? So this is actually tested by the same video. And as you can see here, if we have the ball velocity, or if you had the ball and the Slinky above ground, then that means that there's enough tension force for the ball to stay there, and so the ball and the bottom of the slinky is going to still remain stationary because the elongated this elongated slinky is just making it so that there's enough tension force at the top, which results in the slinky being stationary at the bottom even if there's a weight attached. Thank you. My name is Richard, and that was my lab.